Hi guys, this is about obtaining the matrix for the perspective projection with respect to symmetric and oblique. So in this case, while mapping your vertices of the object, a symmetric projection will be actually mapped to a parallelepiped. So here, this is nothing but a rectangular structured three-dimensional figure. Whatever you have in the form of a symmetric perspective, this is going to be mapped to a parallelepiped. In turn, we are actually mapping it to an orthogonal projection. So whatever data we are having, that will be mapped onto the orthogonal projection. But this one is easy. We can do it just changing the properties of the object by mapping the points. We can do it very easily because the center line, you can see they are parallel to each other. What if we have a perspective projection? Then the problem arises. That is oblique projection. Oblique projection will not have a 90-degree angle. It is having some angle other than 90-degree. We are supposed to map this to orthogonal projection, wherein you can see the center lines are not parallel. So we are supposed to find the matrix in order to obtain this. As you can see, the view is along the z-axis. If I map here, that is oblique to the orthographic, we are going to change the properties of the object, like shearing. Shearing means it's going to change the shape of the object, but both are considered along the z-axis. The main reference is considering a clipping window with minimum and maximum values. We are supposed to make sure that we bring all the points with reference to the center line. This center line is the one which is going along the z-axis. So in this easiest way, wherever we came across the transformation, we used to consider origin. So in this case, what we considered for our frustum was XPRP, YPRP reference. Along the z-axis, all the points for x and y values are same. Everywhere it is XPRP, YPRP. Only the value of z varies. 0 to some value and 0 to some value. So here consider XPRP and YPRP are equal to 0. First case. XPRP equal to YPRP equal to 0. And mapping the oblique projection to the orthographic property will be shearing. So we will be having a shearing property. Now XPRP, YPRP are same along the z-axis. Where the shearing happens is shearing with respect to x over z and with respect to y over z. And there won't be any specific shearing required for z, but we are considering the clipping window. The clipping window is the near face of the perspective projection. The near face will have the z value be equal to z near. So now considering the point where we want to actually calculate to be XPRP, YPRP and z near here. So we have taken 0, 0 and some z near value. So what was the first thing we took? We considered shearing property. Shearing with respect to x and y over z, which means we get to have a matrix for shear over the z parameter. Representing it in homogeneous format, let us take identical identity matrix, and our shearing is x with respect to z and y with respect to z. So xz will get the shear value, yz will get the shear value. This we will represent as zx and this one will be zy. Remaining terms as it is. This is homogeneous, so H0. This will be the shear matrix. Now, what was the point we are supposed to obtain? At 0, 0, z near and taking the homogeneous point, it is 1. xprp, yprp and z near. So this is nothing but we are going to shear the point. So we are going to have a dot product with what? With midpoint of the clipping window to be considered. So xw min plus xw max divided by 2 will give the midpoint of the three-dimensional frustum. Then yw min plus yw max divided by 2 is the midpoint y value for 3D frustum, and z near, we know that the near clipping plane is taken, so z near and 1. So this will be the operation that is required, where we can consider our shzx to be equal to the first expression multiplied by the value minus 1 by z near. I'll tell you the proof. This is what we are supposed to actually obtain. xw min plus xw max divided by 2 z near, and in the same way sh zy equal to minus yw min plus yw max divided by 2 z near. Here the shearing parameters should be chosen in such a way that it satisfies this expression. Means we are supposed to obtain 0, 0 z near value. This can be done when in this shearing matrix, if sh zx and sh zy will bear the values like this. As you can see here, these are the positive terms, these are the negative terms. When we actually perform the matrix dot product, then we get these two terms and we get the term to be equal to 0 and also with respect to the y. So we get 0, 0 with respect to x and y. And due to this, when we multiply with the identity 1, we still retain the z near value. So when you do that, you are going to obtain the required value over the clipping window, that is 0, 0 z near 1. So the shearing parameters are considered to be like this, the negative terms with z near combination. So on doing that, we are going to successfully get this particular representation. Means we are actually bringing the vertex to the center of the clipping window to pass through that center of projection line xprp yprp line. Later condition goes to writing the perspective view projection matrix for these conditions. Now considering this shear matrix to be at the origin with respect to all x, y, z, which means that considering xprp equal to yprp equal to zprp equal to 0. So with this condition, we are actually getting the clipping plane at zprp equal to 0, which is nothing but origin of the z axis. Also x and y are also at the 0 point. So overall on the world coordinate axis, we are setting our clipping plane on the origin. So using this condition, this perspective matrix can be rewritten. According to our condition, ZPRP should be equal to 0. So we get minus ZVP 0, 0, 0, 0 minus ZVP 0, 0. XPRP equal to 0, it is 0. YPRP equal to 0, it will be also 0. SZ as it is, minus 1. Now these are all 0, so 0, 0. TZ as it is, ZPRP equal to 0, 0. And we considered the near face to be the clipping plane. So ZVP, clipping plane is, that is a clipping plane, nothing but the viewport is present on the ZVP area. That location is nothing but Z near. So we will be rewriting this. Here we are considering the near face, so Z value will be equal to Z near. So Z near 0, 0, 0, 0 minus Z near 0, 0. Then you have 0, 0 SZ minus 1. Then 0, 0 TZ 0. This will be the matrix for perspective projection. Now finally, what we have is perspective projection matrix when we have the clipping plane on the origin. Then we have a shearing matrix when we are supposed to transform the oblique projection. So in order to get a matrix, that is M oblique perspective. So oblique perspective, we need to perform the dot product of perspective matrix and the shear matrix. Perspective matrix, just now we wrote minus Z near 0, 0, 0, 0 minus Z near 0, 0, then 0, 0 SZ minus 1, 0, 0 TZ 0. Then MZ shear also we know, 1, 0 SH ZX 0, 0, 1 SH ZY 0, 0, 0, 1 0, 0, 0, 0 1. And we also have the values for shear values. The shear values are having the value minus of XW min, like how I wrote here, minus of XW min plus XW max by 2Z near, same way for Y. So if you substitute the same thing for this matrix and perform multiplication, we will be ending up with the matrix, overall matrix for mapping the oblique projection to the parallelepiped, that is orthographic projection. XW min plus XW max divided by 2, and we have YW min plus YW max divided by 2. Then you have scaling factor minus 1, 0, 0, translation factor 0. At this step, we just have taken the values for a rectangular 3D parallelepiped, right? Now, whatever projections have been generated, they have to be normalized. Normalized means the value ranging from -1 to +1. So this 3D data, that what I can represent like this. Rectangular shaped 3-dimensional data. This has to be mapped to a normalized cube. The normalized cube will be having the minimum value to be -1, -1, -1, and max value to be 1, 1, 1. And we are referring to Z axis along this angle, and y axis on the top face and x axis on the side face. This is same for this case also. We are going to have y axis, x axis and z towards this. So we are supposed to perform a transformation of whatever object that is defined within this to a cube of -1 to +1 range. As you can see here, the view is oriented in the angle of z-axis, that is direction of the z-axis. So due to this, we don't have to translate x and y parameters. I told you along the z-axis line, x and y value will be remaining same as the planes are moving. But as you can see, rectangle to square, it has been changed. That is rectangle to cube, we are going to change, which means there is a scaling factor required. Scaling with respect to x and y in order to perform normalization of the values defined for parallelepiped data. Which means that we are supposed to have scaling matrix with respect to x and y. So when we have scale with respect to x and y, obviously we have Sx at xx, Sy at yy. We don't have to do anything with respect to z, so they remain as it is. So this will be our scaling matrix required over the x and y. Now we already have come across the matrix for oblique to orthographic. Means I have come across the matrix from oblique to orthographic. Next we have to go for orthographic to cube, normalized. So for that one we need a scaling matrix. So overall matrix for a normalized perspective projection. So norm, this is an normalized perspective, is equal to the dot product of scaling matrix with the oblique perspective matrix. So we have both the matrices here, this matrix and this matrix. On performing the dot operation, this you can manually solve. We get minus z near Sx, so obviously here also same, minus z near Sy. Then scaling factor we have for z already, Sz overall, and here it will be 0 because we are considering the origin, and this is 0. At xz we have the scaling parameters, so we are actually performing the dot product, so we end up with Sx into xw min plus xw max divided by 2. Same way Sy yw min plus yw max divided by 2 and Sz, and here it will be -1 from the first matrix. Here 0 0 and here 0 0 0. Coming to the translation, we have 0 0 and here it will be Tz. This will be the overall matrix required for normalized perspective projection over the oblique projection. Next, to obtain the homogeneous coordinates. So extracting homogeneous coordinates xh, yh, zh and h from the known value, that is matrix for norm perspective dot known value is what? X, Y, Z 1 by the definition of the object we know. Using this we will be obtaining the homogeneous vertex values. And once we obtain this, we can easily obtain the projection points. We know xp equal to xh by h, yp equal to yp by yh by h, and zp equal to zh by h. So on solving this xyz multiplied to the normal, we will be obtaining the value for xp, yp, zp as minus z near sx multiplied by x. This can be related with the matrix that we have already, plus sx of xw min plus xw max divided by 2 whole divided by minus z. And a similar representation for yp as well. Yp means minus z near sy into y plus sy of yw min plus yw max divided by 2 whole by minus z. This we will obtain if you perform simple matrix multiplication between these two. You can manually do that. And on the zp you will be getting sz multiplied by z plus tz divided by minus z. So this will actually be the value for xp, yp, zp.